some hints where you can find the right solution when it comes to summarizing a very long document. So uh, let's first take a look at the agenda for this talk. Uh, so what I'm going to do is we are going to go over this general outline, but since some of these things are already covered in the previous talk, I can just briefly mention them or briefly breeze through them. But the general idea is we will first talk about a little bit on evolution of language models, like what are the major strides when it comes to language models and how we reach to transformers. Then I will talk a little bit on summarization. What are the ways you can summarize your document? How do you measure the performance of it? And then as the major talk is mostly about prompt-based summarization, so we will still take a look at how you can summarize a document with Hugging Face. We won't take a look at the training code of it. But yeah, so we will briefly discuss a little bit about this. We will talk about the challenges that you can face with the summarization of long document, and then we will conclude this session. So let's first take a look at the prerequisite that you need to run the code that I have available with me. So you can use any Python version, uh, and it's better if you have Jupyter Notebook kernel or Jupyter Server installed. And as libraries are concerned, we will be using Hugging Face library and Langchain. I don't know how much experience do you have with this, but Langchain is one of the well-known libraries for it's basically used for prompt engineering. You can also do like write your own prompts, but I think it's much easier if you use Langchain for some certain tasks. Um, and Hugging Face library is also something that I don't have to tell anyone about. I think most of us who are actually working in NLP are already familiar with it. Then what else do you need is you need access to one of the chat models, because since you're going to do prompt engineering, you need to either use something like GPT-3, GPT-4, or you can use something like Text Bison, which is available from Google. So in my examples, I'm going to use Google's Text Bison, but as I said, you can also replace it with any other model. Uh, what you can do is you can also, create an Azure or a GCP account. You get access to a couple of free credits and you can utilize the LLMs over there. Or else you can also use some open source LLM like Llama 2 Chat or Mistral Chat. But the issue is these models need a lot of resources. So make sure like you have enough RAM. Don't load it on your machines, but maybe use a TPU VM from Google Colab if you are going to run this. Uh, Now let's take a look at the evolution of language models. So at the very first, in the very beginning, as we also saw in the previous talk, we have statistical models, and they played a lot of significant role when it comes to language modeling. Hidden Markov model is one such statistical model. It basically builds a state transition graph, and the emphasis of this particular model is learning the hidden states, which are not something that you can directly observe in the data, but you can infer them from the data. And then whenever you have to make a prediction for, let's say, your current state, then you depend on the hidden state as well as the previous state that you have seen in the state transition graph. And this is basically nothing but the extension of your Markov property. So, as I said, this model was widely used for POS tagging, name entity recognition, and so on. And I think you can still use it. Like it has pretty good performance. So another statistical model that I can think of right now from top of my head is naive Bayes. I think this is also something which is widely used for spam detection, and it also works relatively well. So it's not like you always have to go with a large language model. Certain problems you can always solve with still these older models as well. The next bigger stride was the idea of word vectors, which is also something that we discussed in the previous talk. Uh, so the idea is exactly same. You take your words and you embed them into a numerical multidimensional space in such a way that you preserve the language semantics. Uh, this idea of word embeddings was then further extended. So there are different variations to it. And then the next extension was to have something like sentence embedding or a document embedding, which is something that you can also use. And there are algorithms like doc2vec or fast text or sentence vectors, which basically allow you to, not only generate an embedding for your word, but you can generate an embedding for your complete document. And then what you can do is you can calculate similarity between those documents. For example, let's say I have certain news articles and I want to calculate if two news articles are similar, are they dissimilar? So to do this, you can always use something like a doc2vec model. And then the next big idea was a sequence to sequence model. And as we talked before, so over here you have something like a encoder decoder architecture. Encoder generates a hidden state, which is then consumed by decoder. Uh, the big idea over here is like the input size and your output size. They do not need to be exactly the same. And this particular behavior makes it pretty ideal for language translation tasks. One thing to keep in mind is these sequence to sequence models, they cannot be trained in parallel. So you have to basically, as the name suggests, you need to train them in a sequential manner. On the other hand, we have a transformers architecture, and this transformers architecture is again based on the encoder decoder stack. But the difference is, as we saw before, you can train this in parallel. Uh, Yeah, so this is how we essentially reach to the large language models. So this transformer architecture is something which is at the core for all the large language models, like your uh, GPT models or Mistral, Llama, and so on. So now we can see there are like lot of language models which are available in the market, and a lot of tech giants also have their skin in this game. So what they do is they basically train a foundational model which has been trained for, let's say, predicting the next word, as we saw before in the previous presentation as well. And then what you can do is you can take these foundational models and then you can fine tune them for a very specific task that you want to perform. For example, let's say you want to uh, use a model for classification, or you want to train a model for summarization, or even for translation. What you can do is you can take these foundational models and you can train them for these specific tasks. So this particular activity of training a downstream training is basically known as task specific learning, and you can train them, as I mentioned, for anything, something like translation, name entity recognition, or for classification. The core idea behind this is that you assume that your foundational model has already done the major task of learning the language semantics. And now that you're going to train a model for a very specific task, you don't have to train the model from scratch. You can just fine tune it. And with less amount of data and less amount of resources, you can still uh, train a pretty good model. Uh, what you can also do is you can do something like low rank adaptation, where the idea is you don't uh, you don't train the foundational model completely. You freeze couple of layers, and for certain layers, you basically replace the matrix weights with the uh, low rank values. Basically, something like you don't keep your weights in, let's say, int64. You use a smaller or a less memory intensive representation of those weights. And what happens because of this is you don't have to you don't have to utilize that much memory for those foundational models for smaller downstream tasks. You essentially end up saving a lot more memory. Uh, what you can do is you can use a library from Hugging Face, which has a support for uh, fine tuning for low rank approximation, low rank adaptation. What I can do is I can also share some code on how do you fine tune the foundational model for using low rank adaptation. But for this presentation, I just want to keep it keep the focus only on prompt engineering. What people additionally like to do is whenever you are doing any task specific learning, they like to add a prefix to the data, which basically specifies what task you are trying to do. And this is especially useful when your foundational model is trained to perform multiple downstream tasks. For example, you have models like T5. You can use this model for summarization. You can use the same model for uh, translation. So what you can do is you can add a prefix which essentially tells the model what activity you're going to perform. And based on this, model basically gives you the proper responses. Uh, are there any questions so far? Okay, then I think we can basically take a look at uh, the chat models. Uh, so the chat models are uh, basically result of a similar task specific learning. Chat models are trained with an intention or with a basically are trained with an intention that they can replicate a human conversation. These models are typically trained in two steps. So in the first step, you have something called a supervised fine tuning. Uh, you have something called supervised fine tuning where you have a predefined data set and you train the model on that particular data set. And then in the next step, you take the same model which you got from the previous step, and then you apply some reinforcement learning. Uh, these chat models are then uh, are something that are widely used for prompt engineering. So one of your example is your chat GPT, which is obtained after doing a similar downstream training for the GPT model. In supervised fine tuning, what you do is you generate a large data set, which includes a lot of human conversations. And this data is basically generated by human labeler. So, and then you use this data to fine tune the model. But the issue with this particular approach or this particular step is that you don't have a lot of manually labeled data, and it becomes a bottleneck very quickly when you want to train a chat model. So what you then do is instead of relying only on the chat data, uh, you apply a little bit of reinforcement learning. In that step, what you do is you collect all the outputs that are generated by the LLM, and then you just rank them. Again, this ranking is something that needs to be manually done, but based on and for this rank data, what you do is you train a reinforcement learning model, you design a reward function, and this step basically makes your language model a little bit more robust. Uh, if you want to try training any foundational model using reinforcement learning from human feedback, there is also a very good library. It's not exactly a transformers library, but I think it's called RLHF from Hugging Face. And with that library, you can basically define your own reward functions. You can define your own scoring algorithms, and then you can fine tune the large language model based on the human feedback. But again, you need to collect this feedback from somewhere. However, what happens if you don't have the training data at all? Uh, in that case, what you can do is you can just take whatever large language model is available to you, and then you can just do a little bit of prompt engineering. Uh, the prompt engineering's goal is basically to provide structured queries to your chat model so that you can get a tailored result. So it can be something like you can tell your large language model to generate a result in, let's say, a JSON format, or you can tell your large language model to classify your data in one of the given classes. So this basically pushes the output of the large language model in a particular direction. That is something that you expect from the model. And as well as it also removes any bias which might be present because these kind of models, they are actually trained on a lot of data. So of course they have certain bias present. Uh, and I think most of you must have already tried these models. So they can be used for classification, summarization. They can be used for chat applications, or also can be used for Q&A. And prompt engineering is pretty good when you want to do a quick POC, let's say low code, quick win solution. And especially when you don't have a lot of label data. So it may happen like you want to train a model or you want a model in production as fast as possible, but you don't have enough training data or you don't have enough resources to collect the training data. In those cases, prompt engineering usually works pretty well. On the other hand, prompt engineering can also be very expensive because all the models like ChatGPT, TextBison, they charge you per token. And as your prompt size and as your number of calls increase, they can get a little bit more expensive. Another issue is data residency. So for a lot of organizations, it is a big concern that they don't want to expose the data to the language models. You can explicitly specify this to most of the cloud providers that you don't want to use the data for training purpose, but still even exposing the data to an unknown cloud service may not be something that your organization may want to do. Uh, Another issue with the LLMs is that especially these chat models, they are non-deterministic. So the output that is generated by these models, especially when it comes to something like a structured JSON, it may not be always consistent. So you may have to take some additional steps in post processing to clean the JSON structure or to check for any inconsistencies if they are present. And then another well known issue is just the model hallucination. So we all know LLMs hallucinate a lot. They make up a lot of new information which they haven't seen in the data set. And this can be a big problem whenever you are working on a production and production applications with some critical data. Uh, any questions so far? I think this much is pretty easy to grasp. Right. So then we will take a look at what you should do whenever you are going to write uh, good prompts, or what is the best way for you to utilize your prompts as much as you can. So ideally, there are 5 design principles which you should usually follow. The first one is you should always assign a role to your prompt. So you should basically tell your LLM what is the role he's going to play for a particular task. It can be something like you can tell the LLM to imagine it. So something like imagine that you are a e-commerce content writer, or imagine that you are a text auditor, or something like this. Uh, it is also very important that you define the output style. If you want your result into, let's say, uh, enough certain bullet points, if you want them as a JSON or a CSV format, so you need to explicitly specify the output style. And of course, you need to be very specific on what you want the prompt to do. what the LLM should be doing. In addition, you should provide some supplementary data if it is possible. You can also add some examples how your output should look like, something which similar to zero shot learning. I won't call it an exactly zero shot learning, but you can show the model couple of examples how your desired output should look like. This always helps model to reduce the hallucination. And then you can add certain conditions like what is an alternate flow if the data is not found. You can instruct LLM to restrict the output, or maybe generate certain null values if you're generating a JSON or something like this. uh, what I will do is I will show you a response that I generated using text Python. So over here we have a prompt for text summarization. As you can see, we are specifying the role in the prompt. We specify that the chat model has to think as it is a financial analyst. We specify the task, which is a summarization. We also specify the style of the output. We specify some conditions like it should only generate uh, 5 data points. So with this, we get a relatively, I would say, relatively good output for summarization. But this only works when you are working with a smaller text for summarization. But what happens if you start working on with a very large document? Let's say the document has something like 50 pages of text or 100 pages of text. How do you solve this particular issue? So we will take a look at that in upcoming slides. So the first thing that I want to talk about is if you're going to look into summarization, there are two ways you can summarize your data. The first method is extractive summarization. So the idea of extractive summarization is that you don't generate any new words, but you basically extract the text or extract the words from the text that you have provided for summarization. And the second is your abstractive summarization, which basically rephrases your text or generates the new words for the given text. We will take a look at an extractive summarization problem. So we will basically use the Hugging Face library for it. And you can use a predefined dataset, something like Bilsum dataset. I have added a link for my uh, notebook. It basically uses this particular dataset, but you can also use some other data as well. Uh, I will show you the notebook in a minute. But before that, I also wanted to talk a little bit about the performance metric. How do you calculate your performance of your summarization? So let's say you have some label data available to you. In that case, what you can do is you can calculate your BLU metric or a ROC score. So both of these metric are pretty similar. BLU calculates your precision, while the ROC metric calculates the recall. Uh, let's take a look at the BLU score for a minute, and I will just give you a very simple example how it exactly works. Uh, let's say that your ground truth is something like the cat is very lazy, and your model predicts something like cat, 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 cat. It just predicts cat 4 times. Now, if you calculate a BLU score on unigrams, then what you effectively do is you divide the number of matches by the number of n-grams in prediction. In your prediction, if you are working with unigrams, you have 4 unigrams, so you will divide the number by 4. And your unigram cat, it appears in both your ground truth as well as in your prediction. So you have a match. And this match occurs 4 times. So essentially, you are dividing 4 by 4, and your BLU score becomes 1. But it is not actually a correct summarization or not a correct output, let's say. And hence, to solve the issue of repeated words, what you do is you apply clipping. So what you effectively do is you clip your n-grams, so that if cat appears 4 times, I will still consider that word appearing only once. So my BLU score now becomes 1 by 4, which is 0.25. Uh, Now, another issue that can happen whenever you are comparing the summaries is it can happen like your word order is incorrect. Uh, let's say you are predicting all the correct tokens, but the order of the words is not proper. In that case, you'll still want to penalize the summary that you have generated. So what you do is instead of calculating the BLU score for unigrams, you calculate higher order n-grams, something like bigrams, trigrams, and so on. And for higher order unigrams, you calculate the BLU score. In the end, what you do is you average out all the scores, and that's your BLU metric. You can do the same with your rogue metric, and with both of these together, you can calculate your F1 score. Uh, any questions so far?
So, Saurabh,
Yeah,
regarding blue rogue metric, right? So,
yeah.
like since they are matching words, right? So, are they also do they work equally well for both extractive as well as abstractive summarization,
Yes.
or there are variants, something extra that might be done?
No. So ideally, the BLU metric works best when you are using it with extractive summarization, because for abstractive summarization, you still need a ground truth, which is having a little bit of, let's say, uh, different wording. So if your ground truth already has, let's say, rephrased text, then maybe you can still use it. But ideally, BLU metrics will work best for extractive summarization.
Okay, thank you.
Uh, right. So now we will quickly take a look at one of the code. So first we will take a look at Hugging Face sample. So over here, uh, I'm not training the model, but I still want to show how to use Hugging Face just to get some summarization result. I assume all of you have already used it, so I don't think I need to go into a lot of details regarding how to use the library, but just a very brief overview. What we are doing is we are creating a pipeline, and for this pipeline, we are specifying a task. So since we are going to do summarization, we specify the task as summarization, and we are going to use T5 model, so basically smaller version of it. So I'm specifying that model, and I'm just creating a summarizer, and I'm passing the document to this, and this will basically generate a result for me. I don't have to do anything special over here, since I'm just calling the model. And for these results, I can, of course, use my ground truth to calculate my road score. Uh, One thing to keep in mind, I think I haven't mentioned it over here, but it's in my other notebook, which is there on the Git. What you need to do is you have to add a prefix to the input document. So you should have a prefix like summarize colon, and then it should have your document text. Uh, the good thing about this particular model is it does not need a lot of memory, but and it uses basically extractive summarization. But the downside is like it will not scale for long documents, because again, the number of tokens which your Hugging Face model will generate, it's very limited. I think it is uh, 1024 tokens, if I'm not wrong, for T5 small. So again, if you're going to use a very large document, this approach won't work. So what should be done? What is the alternative for with us? So the next thing that we can do is we can use Langchain. And within Langchain, you have three methods that you can use for summarization. You can use stuffing, you can use map reduce, and you can use a refine method. I will briefly discuss all three methods. So let's first just look at the stuffing method. So the idea of stuffing method is you pass the entire document in a single LLM call. Uh, Whether this will work for a large document or not depends on the kind of LLM you are using. So even for GPT, there is a version available which works with 8,000 tokens. Same goes with Text Bison. There is a version which works with 8,000 tokens, and I think this should work for your long document summarization. But the out of the box or the default model which works with 2,000 tokens will not work for you because again, your LLM prompts are limited by the size of your input tokens. Uh, the good thing about the stuffing method is it is faster and it is cheaper because you don't have to make multiple calls whenever you're going to uh, use this method. What we will do is we will use a white paper which is available from Google on MLOps, and we will use this PDF and try to summarize this particular PDF. Uh, so let's first take a look at the snippet from for summarization using stuffing method. So what I'm doing over here is I'm just importing all of my libraries. So the most important one over here is load summarize chain. So within Langchain, what you can do is so Langchain has some predefined chains for every task. So you have question answering chain, you have a summarization chain, you also have a chain for generating embeddings and using it for similarity. So within each of this chain, there are basically some predefined prompt text available. So they already write some prompt at a very high level. What you can do is you can also specify your own custom prompts, which is what we will do in this example. But we will still use it as a, let's say, a control block for our code. Other than this, I'm using Vertex AI because I need to use one of the available chat models. You can replace Vertex AI. So Vertex AI is from Google, and within Vertex AI, you can use different models like Text Bison 1, 2, or Gemini. Uh, you can also replace Vertex AI with something like OpenAI library, and then you can have access to some ChatGPT 3 or ChatGPT 4. Or you can also replace this with any of your open source model. So this is something which is completely dependent on you. Whenever you run this code, you can change this as per your needs. Then, yeah, so I'm just initializing the LLM over here. I'm specifying the version that I want to use. I download the PDF from internet. So nothing too special. So in the stuffing method, since we are limited by the prompt size and I cannot, summarize the entire, I think 30-page PDF, 30 or 40-page PDF in one shot, what I'm going to do is I will just summarize first three pages for now. And we will see how to summarize the complete PDF in other methods. So what I do is I basically download this PDF and then I create a prompt. So as I mentioned, uh, you can create your own custom prompt, or you can let the LangChain design the prompt for you. So over here, I'm creating my own prompt. So I'm specifying my prompt template. I'm stating I want to create a summary, and my text for summary is basically delimited by triple back quotes, and I want that text in a bullet points, and it should cover all the major points of the text. What I do is I create a prompt from this template, and then in this, I create a load summarization chain object. I pass my LLM. I specify the chain type, which is now stuffing, and I provide the prompt. And I also specify what is the document variable name. So document variable name is basically something which will be replaced by LangChain with the text from your document. So over here, the document variable name is text, and LangChain will replace this with the text from the PDF. and then I just call your chain.run. I run it for only 3 pages, and this is the output that I get. So as you can see, you're already getting uh, I would say well enough summary for the given text, but you will see that the text is not complete, and this is because you have a fixed number of tokens for your input uh, text or input prompt, but at the same time your output also has a fixed number of tokens that it can generate. The problem with this stuffing approach, as I said before, is you cannot summarize the complete PDF. You can only summarize a couple of pages as long as you can store that particular text into your prompt template. So, what is the alternative to this? The alternative is you can use something like MapReduce. So, I think everyone already knows the concept of MapReduce, but just to reiterate, you have two stages in this particular approach. In the map approach, you divide your complete PDF or your large document into smaller chunks, and then you summarize each of this chunk. And then in the reduction part, you take all of these summaries, you stack them together, and then you generate a final summary. The downside of this approach is that it needs a lot of calls. Like you end up making upwards of 30 or 40 calls just for a single document summarization. Uh, Let me actually show you the changes in the code that I made and how does the output looks like. So now you have two prompts. The first prompt is to summarize the chunk, which is your map prompt template. And as before, I created a prompt out of this. I specify the input variables. And then I have a second prompt, which basically does combination of all of your summaries and then generate a final summary. And again, for this, I'm creating a combined prompt. Finally, in the load summarization chain, I pass my model. I specify my chain type as MapReduce. I specify my map prompt, and I specify my combined prompt. And if I say this, if I state something like return intermediate result steps to true, then it will also return me all the intermediate results that were made in each LLM calls. This is useful whenever you are going to debug your model or whenever you want to debug your results. So this above code, it basically makes 36 calls in total, 35 one for each chunk, and the final call to merge all the summaries. And this is how the summary looks like. So now this summary that you are looking at, it is the summary of the entire PDF. Um, there is still one issue to MapReduce, which I haven't talked yet, which I will briefly discuss now before we move on to the next method. So let's say your document that you want to summarize, it is very, very, very big. Uh, what happens in that case is in your map step, you can create multiple summaries. But in the reduce step, when you create your prompt and append all those summaries into that particular prompt, it might be possible that this prompt might overshoot your LLM's input size. And this is something which is very much feasible when it comes to a long document summarization. So to overcome this, we have a third approach. And this approach is basically known as refine or refinement. What you do in this step is you again make two calls, but in the first call you summarize the chunk, and in second call you provide a summary that has been generated so far and the summary that you have generated for this chunk, and then you create a new running summary. So essentially you make one additional call whenever you are generating a new summary, whenever you're processing a new chunk, and this basically runs in a sequential manner. So same as before, you you have two prompts. The first one is a question prompt. This is basically to summarize the chunk. And then you have a refine prompt, which basically is used to summarize the running summary so far and the prompt that you have and the summary that you have generated in the recent call. Uh, and the rest of the code is pretty much same. You specify your chain type as refine. You specify your question prompt. You specify your refinement prompt, and then get uh, and then you get some generated summary. This is how the refine method works, and these are like the well-known three methods from Langchain when it comes to summarization of large documents. Uh, Now, I will actually share a little bit about my personal experience when it comes to summarization because we had a use case where we had to summarize a large document, and we found out that, like there are a couple of issues with the refinement method as well. And the first and the biggest issue is you are always limited by the output size of your LLM. So your LLM can, let's say, generate 1024 or 2048 tokens at a time. So even if you use something like a refine chain from Langchain, what is going to happen is your final output will have at max 2048 tokens, and it may not cover all the information. For example, it doesn't make sense to summarize a document of 10 pages in 2048 tokens and summarize a document of, let's say, 500 pages in the same uh, token size. So what we ended up doing was we created our own model. So we had two-step process essentially. We developed our own model for chunking to create logical chunks rather than creating a chunk based on text size. And I think there are a lot of models that you can also find on internet, which basically does document analysis and breaks your document into your headers, your paragraphs, which are the logical sections, and so on. So we trained a similar model. We trained a model which can basically classify paragraphs together, which are similar paragraphs together. We gathered a similar chunk, and then we pass that chunk through LLM. And this particular chunk will generate a part of summary, and then we don't refine this summary again. We just keep it as it is, and then we redo this process iteratively. And this is something that we finally settled on, which worked pretty well for very large documents. I cannot actually show you the source code, unfortunately, for this approach because it's it's a company's project. But what I can do is I can share the document classification or basically document extraction algorithm because that's something which is open source, and I will also share that uh in the Slack. So finally, what we have seen so far is we had a very high level introduction on document summarization, how to summarize it, how to work on long document summarization, and precisely with prompt engineering. I would like to show you some more code or focus some more on model training in upcoming sessions. But the first session, I wanted to keep it as simple and as simple as possible. Uh, right. And then I'm done. Any questions?
So, Saurabh, any suggestion on how to make a call that which LLM we should use for summarization tasks? Like any
So
website
it
or
actually depends on so it completely depends on your company's infrastructure. And to be honest, because if you're in industry, it's very difficult to say, like, if you're starting from zero, if you don't have any LLM or any infrastructure present from the in the initial go, then you can do certain tests, see which one works best. And these tests could be something like just we saw calculate BLU score, check what performs best for your use case. But if you have an infrastructure which is present on a particular cloud provider, then I think your options are pretty much limited. what I have personally seen is Google's original models, at least the text bison one, was okay when compared to GPT. GPT was definitely much better than Google, but now the latest model, which is Gemini, it's actually performing neck to neck if you're looking at the core, like the raw performance.
Would you suggest using open source models like self-hosting?
I Yeah, so this is something which is an interesting question, and it depends on the scale of data, the number of queries you are going to make, because LLMs are much so using a service from Google, from Microsoft, or even from Amazon. I think Amazon has Titan, if I'm not wrong, Titanic or something like this. But these services are much cheaper than hosting the model on your own. If you are going to make, let's say, I don't know, couple of thousand calls or 5,000 calls per day or something like this. But if your calls are very, and it also depends on your prompt size, how many tokens you are utilizing in one call. But if your number of calls are very high, then it might make sense to host them yourself. So there are models like Llama Chat. I think Llama 2 Chat, which I have tried, it also works pretty good, but it needs a lot of resources to keep them hosted. So if you have a lot of calls, you need to do something like a cost analysis and figure out what works best, because even hosting is very expensive. But the good thing is you don't have to use GPUs for this.
So, if I understood right, the crux is that if you have like decent traffic, not much, you're better off using the hosted services of cloud providers rather than
Yeah.
self-hosting. Cool. Thank you.
Any other questions? So I think then this also ends my session.